Hello. My talk today is about vectorization avoidance in data parallel Haskell, which is basically kind of a variant on the flattening transformation. For those of you who have been at ICFP yesterday, Ben talked about it, and we had talks about, in the context of Nestle on GPUs. This is joint work with Manuel Chakravarti, Ben Littmeyer, Roman Lechinsky, and Simon Payton-Jones. Again, for those of you who have been here yesterday, this example will look familiar, and in particular the picture. As a running example, I will also use in-body computation, but to keep it a bit more simple, I actually use the naive version of an in-body computation, where you calculate the forces just by basically taking every possible, in each step, every possible combination, and then calculate on that. But for us, in the context of this talk, it's really not important whether we have irregular or regular parallelism. You wouldn't do that, of course, if you wanted to actually get some performance. So parallelism is basically, we have these parallel arrays here. One of them is a parallel array of math points, and calc accels returns a parallel array of accelerations for each point, the forces which we will work on this array. The actual work happens here, so this basically takes for each point every possible combination and calls this function accel, which does the actual work. And then we have another source of parallelism. We sum up all the x and the y components to get the force for each particle. The distributor removes the parallel array comprehension and will replace the parallel application of sum p with a call to parallel max p of a parallel sum p. So we have the nested parallelism here. Similarly, it will do something like calling accel with a step with 3, extending the data points so that it basically matches up. As Ben explained yesterday, this does not actually happen. Those arrays are not really copied, so it's not as bad as it looks. But just basically on the language level, intermediate level, that's what happens. Now, to get rid of the nested data parallelism, what happens is whenever we have a map P of an already parallel function, it will be replaced with, if that's already a built-in function, with a segmented version of this function. So segmented sum P, which takes a segmented array and computes all the segmented sums. And similarly, it replaces the map accel with a lifted version of the accel, which has to be generated because accel is not a built-in function. And it has to flatten the data vectors to do that. So let's have a look at, as I said, accel first has to be generated because it's just a sequential function that takes two mass points and calculates the forces. So what happens is, for the lifted version of accel, every scalar variable, every scalar argument is replaced by a parallel vector. And here, this notation basically, slightly cheated, is here to indicate that whenever we have a parallel array of non-primitive type, the actual representation type is different. So if we have a parallel array of pairs, it's mapped or eternally represented as pair of arrays, array of lists as a list of arrays, and so on. So we have this transformation of data structures going on, and the functions have to be able to deal with that. All primitive all operations were basically replaced by their lifted version. And in case of first order for applications of functions, what this really is just a parallel, a flat parallel zip with or map. So nothing interesting here. So this happens for the whole program. And what you can see, of course, and what has been mentioned several times yesterday, also in the context of other work using this Nessel model, is that this transformation generates a huge amount of superfluous traversals, intermediate data structures, and so on. So straightforward vectorization as well now produces poor code for general architectures. Now, this problem of basically additional traversals and so on is well known, and we know that Fusion can help us to deal with it. And since we need Fusion anyway, because DPH is basically a collection-oriented, has a collection-oriented programming model, the programmer has to use all these map piece, sum piece, and so on to express parallelism. The obvious solution would be to use Fusion to kind of repair the damage the naive transformation does. So if we have such a parallel set computation, the simplifier, because these are all first order fully full applications, replaces it with the flat parallel zip width, and then Fusion should produce something like that, just zip with 3, which basically does not produce any intermediate data structures at all. Unfortunately, even for fairly simple functions like Excel, if you look at the data dependency graph, there's a lot of sharing going on. And for Fusion, we rely on inlining. If we have sharing, it doesn't really work properly. So even with simple functions like that, Fusion doesn't work as well as we want to. And once we have something like a recursive function, inlining in Fusion does not work at all. So there are clear limits. And our first approach basically kind of to generate naive code and then try and fix it later by using optimizations like Fusion only helped so much. It doesn't really result in sufficiently efficient code. So the other way would be basically, well, let's try and spend some time on analyzing the program and produce more efficient code straight away. Because what we really want to do, whenever we have a sequential subcomputation like this, which we want to live and need to live in the parallel context, we want to leave it intact and not kind of break it together and then later spend all the effort to piece it together again. So the way we do that is whenever we find such a computation, we encapsulate it by basically lifting it into a function, and then now here we have a purely sequential function which we can leave intact, and because it takes 2 arguments, we basically lift it simply by passing it to zip width, and do not have basically the need to fuse that later is gone. Now, one problem is if we do that for all purely scalar sub-expressions, there is one problem I haven't, one kind of special case I haven't told you about. If we have a conditional, like a case expression or an if expression, the way lifting Nessel works is that it takes basically all the argument vectors and splits it into all the values which, for which the condition is true, those for which it's false, processes both separately and then joins the results. On an SEMD machine, that's actually necessary because we can't execute 2 separate programs, 2 different programs simultaneously, but for most of our target architectures it's not necessary. The second reason to do that is if branch and then branch, the then and the else branch are different in work complexity, if you leave the if together, then you might have a load imbalance. So by splitting it, you get perfect load balance. But everyone who's done a bit of parallel programming knows that there's no way for most if expression that the additional work you're doing by kind of copying it, redistributing will ever pay off. So we actually want to leave conditionals intact, even though that will may lead to some load imbalance. Because if you look at it, load imbalance only gets to be a problem if, for one thing, the two branches like one of the branches is really expensive, the other is not expensive, and also the distribution of the values in the vector is skewed. And I try to basically construct pathological cases where this is a problem, and it's really hard to do so, because memory access, just touching the element to check whether the condition is true or false, is so much more expensive than even fairly expensive arithmetic operations and so on, that it's cheaper to execute the operation straight away. So if both branches have a constant work complexity, pathological cases are hard to construct. It's different though for recursive functions. If one branch is recursive, we could basically, one could be the Ackermann function, and then obviously you would get a lot of load imbalance. Now I think there's no real, even for recursive functions, you really don't want to redistribute in every iteration. So usually what you would like to do is kind of split it up in a recursive function that's left intact, and there's a couple of iterations, number of iterations, and then only redistribute every now and then. And you can do that just we can add a compiler option which tells the compiler whether to actually vectorize a recursive function or leave it intact. So how do we identify those sequential sub-expressions which we want to encapsulate and leave intact? First, if we have the abstract syntax tree, we need to identify any nodes in the tree where parallelism might sneak in. This is a bit more complicated than it looks, because these nodes might have scalar type, but they might call a function which internally triggers some parallelism. But it is possible, and then we simply need to basically, once we have those nodes identified, they kind of pollute the whole way up to the root of the tree, and now we can find all the non-trivial sub-expressions which we want to leave intact. We encapsulate them, and then we run basically vectorization, classical vectorization, just whenever vectorization encounters such an encapsulated function, it simply passes it to map P or skip P, whatever it needs depending on the arity. And so let's have a look at some benchmarks at how this compares to fusion. So as a fusion method, we use ring fusion, which is pretty good and really catches most cases. So for this simple function, you would expect fusion to work as well as vectorization avoidance, which doesn't break up the expression. And looking at the core, we could see that that actually happened. Surprisingly, vectorization avoidance was still slightly faster than fusion, because the code produced by vectorization avoidance was simpler. So there is no additional traversal here, but it's just simpler code. The same for this function, which calculates the distance of a point to a line. The difference is a bit less because, and that's basically because we have more complicated data types. It's pairs of arrays in parallel. Surprisingly, once we feed those functions into a wrapper, here zip with p and then sum p, the difference between vectorization avoidance and fusion is much bigger, because it turned out that vectorization avoidance, because it produces simpler code, plays really well with the fusion machinery we still have and we still need, because vectorization avoidance can never get rid of things like sum p and so on. Vectorization avoidance really only avoids those cases which were introduced due to the transformation in the first place, and not by the programmer writing in his collection-oriented style. The previous case, I'm sure we can tweak fusion so that it would actually basically cover that, but the point is, it's just more stable and more reliable by not doing all these things. For a simple condition where load imbalance is not a problem at all, we see there's a huge difference between vectorization avoidance and full vectorization, because, I mean, it was clear looking at the code that doing the whole packing and combining is a bad idea for things like that. And even for a function where there is load imbalance, there's still a big difference between vectorization avoidance and fusion, but we can see that, not surprisingly, because of the load imbalance, vectorization avoidance doesn't scale very well. With a simple recursive function, I don't even have the numbers here for fusion, because it's really 2 orders of magnitude slower, because it has to redistribute in every step, which just does not work. So what we can see here, so we have this, in here basically it's very high load imbalance, and a simple way to kind of counter the load imbalance was here by randomizing the imbalance array by kind of applying a semi-random permutation on it, applying the recursive function, and then back commuting basically. So what I want to say is that usually, even if there's a load imbalance, there are often better ways to deal with it than brute force kind of flattening load imbalance. So as a conclusion, I think vectorization avoidance is very clear. It leads to significantly more efficient code. And interestingly, even though we put more effort, in some sense, in kind of analyzing the code first, it actually leads to a speed up in the compile time, because we mark so many. So the additional analysis is fairly cheap. And as a result, we mount many of the sub-expressions as scalar, so the vectorizer doesn't even have to touch it. And inlining and fusion is not cheap during compile time. So basically, from across the board, it reduced compile time by about 20%, and also the size of the executable. And vectorization avoidance is definitely more stable and more powerful on the lifted code. Just on the lifted code, as I said, for the regular things we still need fusion, and there are cases fusion can deal with, vectorization avoidance doesn't deal with it. In the paper, you can find the formal definition of this transformation, which I only kind of explained in a very, very superficial, intuitive manner. And that's about it. And I'm tired. It's 11 o'clock.